In this video, we're going to look at polyprotic acids. Polyprotic acids are just acids that can produce more than one hydrogen ion in solution. Protic kind of refers to a proton, which is a hydrogen ion, and poly means many. So a good example might be something here like phosphoric acid. Phosphoric acid looks like it could have 3 hydrogen ions produced in solution. Now here's what happens. We should know phosphoric acid is weak. It's a weak acid because look at those K values. They're all very small. Notice also that they continually get smaller. So dissociating the first hydrogen has a Ka value of about 7.5 times 10 to the negative third. And then I dissociate the second hydrogen, and then finally the third. Losing the third hydrogen has a K value of 4.8 times 10 to the negative 13th. That's so small. I mean, even 10 to the negative 8th is ridiculously small. Sometimes people assume that you put phosphoric acid in water and it just, bingo, gives away all 3 hydrogens at once. And that's really not what happens. It's like a progressive loss of hydrogen. And as I compare these K values, I notice that this first dissociation, this is the largest K value, so it really is the most significant source of hydrogen. Just the dissociation of the first hydrogen ion. Because then look how small the second 2 K values are. These K values are so small that, to be honest with you, this is insignificant. The concentration or the amount of hydrogen that we would get from these second and third dissociations is insignificant. It's so small that, to be honest with you, this can kind of be a good thing. Often when we calculate the pH of a polyprotic acid, especially something like this that might be a weak acid to start with, we don't need to set up like multiple ice tables. We're just going to set up one ice table and we'll use the first K value. If I really wanted to, I could calculate the amount of hydrogen that I get from the second dissociation and the third dissociation, but it is so small that it's really insignificant. If you want to do that sometime, stop by and I would be happy to walk through that with you. It's so small that it doesn't change the pH. The only dissociation that really contributes any significant or measurable hydrogen is the first dissociation. And so again, often if I wanted to set up an ice table and calculate the pH, I would only need to use the first K value. The second 2 so small, the amount of hydrogen that we produce is insignificant. So now they give us this comparison then, relative acid strengths. So that first acid, H3PO4, that must be the strongest acid, the most likely to release its hydrogen. And then when I get to the final particle, the hydrogen phosphate, the HPO4 minus 2, yes, that guy can act as an acid and release hydrogen, but the K value is 10 to the negative 13th. It's such a weak acid that, again, we really don't even consider it when we calculate pH. Now, word of warning, this is a little different than something like a strong base. Polyprotic acids are often weak acids. Do you remember we did this one earlier? This was a strong base. We had the barium hydroxide forming barium ion and 2 hydroxide. And in that case, this was a strong base, which means it dissociates 100%. So, for example, let's say this started at like 1 molar, then I get 1 mole of barium ions and 2 moles of hydroxide. And then when I finally did the calculation for pH, I had to take this into consideration. that it dissociates 100%, and I get 2 hydroxide ions, or 2 moles of hydroxide per liter. That's not going to be the situation with these weak polyprotic acids. If I had a 1 molar solution of phosphoric acid, I do not get 3 moles of hydrogen. I don't even get 1 mole because even the first dissociation is so weak that we'd have to set up an ice table for a weak acid, but we'll only include the first dissociation. And we'll use that Ka1 to figure out how much hydrogen we would get, and then we would be able to figure out the pH. So again, just be a little aware that these are different situations. The phosphoric is a weak acid to start with. Even the first dissociation is weak. Different than something like this strong base, where yes, if it's a strong base and it dissociates completely, I will get, like in this case, 2 moles of hydroxide per liter. Okay, so let's look at a very common acid, sulfuric. Sulfuric is a polyprotic. H2SO4 has 2 hydrogen ions available to produce in the solution. So they're showing me then the 2 dissociations and the 2 K values. One thing I noticed right away, Ka1 is big. Ka1, the dissociation constant for the first hydrogen, that's pretty big. 10 to the third. The first dissociation is strong. But then look what happens to the second dissociation. 10 to the negative second. This is weak. Sulfuric is kind of a special acid, so we should pay a little extra attention to sulfuric acid. It is polyprotic. Often polyprotics are weak acids, but with sulfuric, the first hydrogen is actually strong. So you're always told that sulfuric is a strong acid. Only the first hydrogen is strong. The second hydrogen is weak. So here's what people will do, and this is wrong. Okay, so word of warning. This is wrong. They've always been told sulfuric acid is a strong acid. So if I had sulfuric, they want to do this. They want to do H2SO4. They want to break it into 2 hydrogens and the sulfate. So if by chance this started at 1 molar, they want to use this then as 2 molar. And then the sulfate would be 1 molar, but we don't really care. So then when they do pH, they'll go opposite log of 2. And that is wrong. It's wrong because only the first dissociation is strong. The second dissociation is weak. So when we calculate pH, we actually only need the first dissociation. The amount of hydrogen we get from the second dissociation is very minimal. So this whole thing is bad. Sad face up here. That's a sad face. That's wrong. Okay, so let's figure out the right way to do the pH of sulfuric acid. I should leave this up here for a minute. Okay, let's look at the strong acid part. So here's the strong acid. The first step is strong. The sulfuric acid dissociating to form 1 hydrogen, and then the hydrogen sulfate ion -1. Okay, so if this is 1 molar, then I do get 1 mole of hydrogen and 1 mole of hydrogen sulfate, which I don't really care about. That's not going to affect the pH. So in this case, I really can just go pH equals opposite log of the hydrogen concentration, 1 molar. The opposite log of 1. Ooh. pH is 0. Here's another thing. I mean, like sometimes people hear the pH scale goes from 1 to 7, or 1 to 14. And so they'll get like a pH of 0. And they'll be like, ooh, I don't know if that's okay. Oh yeah, that's fine. You can have pH values that are negative. I mean, think about concentrated acids usually come well above 10 molar. If you go opposite log of 10, 12, 15, you can have negative pH values. So don't freak out if that ever happens to you. That's okay, or in this case, it's okay to have a pH of 0. Highly acidic. The first dissociation is strong. So now for kicks, let's check the second dissociation. So now let's do the weak acid part. The second is weak. The hydrogen sulfate dissociating. I'm going to put that as a double-sided arrow because it's weak. I'll leave the water out because we're not going to use it in our final calculations anyway. And sulfate -2. Okay, so for a weak acid, we set up an ice table. The amount of hydrogen sulfate is 1 molar. It's produced in the first dissociation. It's the other byproduct. And I do get 1 mole per liter. So this is going to go in as 1. What else do I have present? I do have some hydrogen. I do have some hydrogen from the first dissociation. So both products in this case are not 0. This guy's going to go in as 1 molar. But I do not have any sulfate ions yet. So I did have some products from the first dissociation. I already have a little hydrogen. Let's see how far forward this goes. I should produce a little more hydrogen. Okay, so we'll call it X. This is going to go down. These will go up. Plus X. So I'll have 1 minus X. And again, I already have 1 mole of hydrogen, but from the second dissociation, I should get a little more. So we'll say 1 plus X. And then sulfate is just X. Okay, so we have the K value. Ka2 for the second dissociation is 1.2 times 10 to the negative second. That equals products 1 plus X to the first times X to the first all over 1 minus X to the first. All right, we haven't had one that looks like this for a little while, have we? In this case, we're going to take our products from the first dissociation and we'll sub those into the second. So I do have some hydrogen sulfate formed, and I do have hydrogen from the first dissociation. But if we figure out X, that'll tell us how much hydrogen we get from the second dissociation. Now that K value is small. I don't feel like solving this for the quadratic equation. So again, let's try the 5% rule, but let's really simplify this. I mean, let's just get after it. Whatever X is, it's going to be small. The K value is small. So are we shifting forward? Yeah, but not by much. So let's get rid of both the X's, the minus X and the plus X. How nice is that? Because then watch this. Oh, this is really nice. How about X just equals 1.2 times 10 to the negative second? That's really small. I mean, that's really like 0.012. And so again, if I wanted, I could kind of think about the 5% rule. When I did my math, I subbed in like hydrogen sulfate or hydrogen. I just used them as 1. Yes, they're going to change, but not by much. Like 0.012. That definitely satisfies the 5% rule. 5% rule. Check. I thought about it. I qualitatively checked the 5% rule. I just wanted to make sure that X did come out to be something small. So that like 1 minus X doesn't differ from 1 by more than 5%. Okay, so the only ion that I really care about here is the hydrogen, if we're calculating pH in the end. So X then is going to get plugged in right here. So this is the total amount of hydrogen in the solution from both dissociations. So now watch what happens if I do pH. pH equals opposite log. The total amount of hydrogen is 1.0 1, 2. Oh. That's pretty small, isn't it? So if I plug this in, I get a pH of like negative 0.0052. Okay, so now this is if we follow all the rules and if we're like perfect little chem people and we figured out the amount of hydrogen from the first association, and then we do an ice table to figure out the amount of hydrogen from the second association. Because the second is weak, I have to treat that a little differently. The total amount of hydrogen in the solution is 1.012 moles per liter. Look at the comparison in pH values. I mean, if I compare these two, the amount of hydrogen we got from the second dissociation was virtually insignificant. It was so small. I mean, did it change my pH? A little bit, but it was so small that, to be honest with you, make note of this. For sulfuric acid and sulfuric acid only, if you have to calculate the pH of a sulfuric acid solution, you can ignore the second dissociation. Did you catch that? Just for sulfuric acid, because the first dissociation is strong, that it provides the most, by far the most significant source of hydrogen. The second dissociation is so weak that the change in pH is insignificant. You can really just go opposite log of that molarity. Now again, the common boo-boo people will make is that they'll do this because they've always been told that sulfuric acid is a strong acid and it looks like there's 2 hydrogen. But you're hearing it now. Only the first dissociation is strong. The second is weak. So don't multiply the molarity times 2. Just go opposite log of 1 molar. And they're totally going to do that, I would assume, on the AP test at some point. There was a multiple choice question on one of the last versions that was supposed to be really easy. And they just wanted you to know that with sulfuric acid, only the first dissociation is strong. So treat it kind of like, HCl. There's only 1 hydrogen that's highly soluble or ionizable. And then you should always get this one right. You do not need to do that ice table for the second dissociation. It's so weak that it's insignificant. But remember, for sulfuric acid only.